do modifications at your city parks, maybe you need to consider it. And kind of get a grassroots effort to get the city to include dark sky compliant lighting in their next construction project for Gateway Park. So you might see something on our Facebook page, and that's a little background information on the thought behind it. So thanks, Sarah, for getting this started, and it turned out to be a nice win for everybody.
And then you have for the rest of the city, too?
Well, you do see it in the new installation of streetlights. They're normally pointed down. They're normally LEDs, so slow progress is being made. A lot more to be done. Okay, we're ready to go. Okay, thank you. Well, good evening, everybody. My name is Bruce Campbell, and I'm the president of the Fort Worth Astronomical Society. It's a pleasure to have you all here. It's a very big crowd tonight. I guess it's because you all heard that Paige Becker might be coming tonight. Okay, Paige Becker, the first round draftee for the women's NBA basketball team, is coming to Dallas.
Nobody knows that but you.
Yeah, I guess I am the only one. Well, anyway, for those young at heart and who do that, I think that's kind of fun. Bad rumor, but not true. But welcome her to the WNBA. I think it could be a good time to run through the slides. So, Christian, let's have it. Am I supposed to stand over here? Okay, so do we have any visitors with us tonight? Well, hope people are online or visitors, but yeah. TJ, stand up and tell us your story.
I'm TJ. My name is TJ. I joined the club last year, actually. I haven't actually been to a meeting in person, so I've been online. You probably see me around every so often, but I decided to actually come because I was working from home today. That's good.
Very good. Welcome.
Thank you.
All right, let's go to the next slide. Okay, so our new members since last month, any of those folks here tonight? Well, we welcome them to the club, and when they show up for their first meeting, we'll find out who they are and find out what their history is on astronomy. Let's go to the next slide. So as we talked about before, the club was founded in 1949 and we've been going strong ever since. It's kind of fun that we have 421 members, actually live people who are part of the club, with a wide range of experience. For those people that retired and decided to get into astronomy in a big way, all the way up to those that have been doing astronomy and optics for decades. So welcome. And you find that most of the folks in the club are willing to help, and you see this especially on our email forum that we have on e-groups. Somebody will put out a question like Tom Roth did on what's the best focal length for Smith-Cassie grain, and a lot of encouraging, helpful comments came back. We're also a nonprofit organization, so feel free to make a donation at your convenience. Let's go to the next slide. So our resources, we do have the dark sky site called Rising Star Observing Area in Eastland County. We also have access to the Thompson Observatory down in Keene, Texas. We have a wide variety of telescopes. As I mentioned last month, we do have both refractors and Smith-Cassie grains out at Rising Star for use. We have a membership handbook. It used to be called the new member handbook, but it's really our membership handbook. And we have a number of online resources. Let's go to the next slide, which include our website at fortworthastro.com. We've got a few pages under construction. Make sure that we comply with some of the copyright rules, but it'll be done in the next month or so. We also have a Facebook page that's getting quite a few views and followers. We post all of our meetings, general meetings on YouTube. It's a great way to keep going back to see what our speakers had to say in meetings past. And then the last two are our e-group forums or email forums that talk about just main astronomy things or the astrophotography special interest group, and that keeps us going. Fortunately, we have a good speaker for tonight's presentation. They're going to talk about the Solar Dynamic Observatory. So I'll turn it over to, so Dean Pesnell will be our speaker tonight, so let's turn it over to him.
Hi. It's been almost a year since I was down in the Dallas-Fort Worth area where I was watching the solar eclipse. I hope you all got out to see that. I am unable to share my slides. You have sharing turned off. So I don't know how to do a presentation without sharing. Is there any way we can fix that?
Yes, stand by. He's working on it right now.
Okay. I'm Dean Pesnell. I'm the past project scientist of the Solar Dynamics Observatory. I retired a couple weeks ago and I'm trying to figure out whether I want to play guitar like Jim did up there, although he looked like he was only tuning while I was watching him. Or whatever. But it's always good to talk about the Solar Dynamics Observatory. It's one of the greatest satellites that NASA's ever flown, and nope, still can't do that. So our goal, when I give this talk in a more casual setting, I often call this astronomy for people who sleep at night, because the idea is that I don't worry about light pollution with the sun. I can go outside, and as long as it's not cloudy, I can actually take pictures of the sun with cameras and telescopes on the ground. The reason we need to go into space is because to look at the sun, we really need to be looking in wavelengths that are inaccessible from the ground. And these are the extreme ultraviolet wavelengths that are very short, less than 100 nanometers or 1,000 angstroms. They're absorbed completely by the Earth's atmosphere. And the cool thing is that creates the ionosphere around the Earth. It heats the atmosphere of the Earth, causing satellite drag. So the study of the sun and its extreme ultraviolet emissions allows us to also understand the upper atmosphere of the Earth. And so this is part of the Living with a Star program at NASA, where we study the sun to also understand the Earth. And so SDO is designed to look in the extreme ultraviolet and reveal details about the corona. It looks at the visible light to do the Doppler shift as across the disk of the sun. So if you can see an image, you can see waves moving across the sun. We can measure the magnetic field of the sun across the disk of the sun, and we also measure the extreme ultraviolet irradiance, or just the total sun as a star, brightness of the sun in the extreme ultraviolet wavelengths. How's the sharing go? Oh, I see sharing has come on. Okay, so, yeah, do that. Okay, can you see my slides now?
Yes.
Okay, so let me get my... All right, so I already started out. All right, so here is the sun in the extreme ultraviolet. This is a helium line at 304 angstroms. I'm sorry, I'm an old codger. I've worked with angstroms for a long time. The advantage of angstroms is it's the right number of decimal places. So it's easier to say 304. than it is to say 30.4. So if I slip and don't use nanometers, it's just a habit. Okay, when you're doing astronomy from the ground, you often do filters such as the Johnson UBV or the narrow band Stromgren filters, but they don't measure the magnetic field of the star. The only way to measure the magnetic field of the star is to use polarized spectroscopy and to measure the Zeeman splitting that is caused when a magnetic field line threads through the solar plasma. And we can use this, an imaging spectrometer to look at the surface of the sun, and that also gives us the Doppler shift, because to measure the magnetic field, we measure the splitting of the spectral line. It looks like it becomes two lines, and at the same time, we have to measure the center of that, and that gives us the velocity. So we get 2 for 1 when we're doing the magnetic field. I talked about the extreme ultraviolet a little bit, and here's a spectrum that shows the brightness of the sun as a function of wavelength from very long wavelengths out in the infrared all the way to the short wavelengths, 10 nanometers, which are roughly going into the short X-rays. And on top of that is the thermal black body, which you're well familiar with from looking at stars. And then the Doppler shift measurements are made where the HMI line is shown. And here is an example of why we study the sun. See, can you see my pointer?
Yes.
When I around, okay. This is where half of that line right here, there's 3 lines, 1/4, 1/2, 3/4, and then black means no radiation of that wavelength gets below that. And so if you look at the halfway point, you can see where the different kinds of radiation is absorbed in the different parts of the Earth's atmosphere. So here's where the EUV is absorbed, all up here around 150 to 200 kilometers of altitude. Here's where O2 is absorbing the mid-infrared, and here's where ozone is absorbing the ultraviolet that we know causes sunburn. And so all the O2 photodissociates, creating O, and then that O creates ozone. So this is where we get both the upper layer and that lower layer.
Ignition and
here's our
liftoff of the Atlas
beginning of our
V
mission.
with the Solar Dynamics Observatory, learning why our star is changing our
And
life.
the cool thing was that soon after launch, we see a shadow there, you see a wave moving up away from the rocket. That was a gravity wave moving along the about 10 kilometers altitude. And if you've ever seen a sundog, we were able to see a sundog during the launch, and that wave went out and shook up the ice crystals that caused the sundog and caused it to disappear. So SDO was the first launch to, the first man-made thing to cause a sundog to be disrupted. And so we were happy that we started with a very nice launch, and we've been up there for 15 years. We're in a inclined geosynchronous orbit, and here's an example of the orbit, and there's the colors that sweep in and out help the engineers know what antennas they can look at for communications, so I wouldn't worry too much about them. But the important thing is SDO spends most of its time out over the Pacific Ocean. It comes up over Mexico, and then barely gets over northern Mexico before it returns. And then we have a dedicated ground station in White Sands, New Mexico, that's in constant contact with the spacecraft. And if you want to see how difficult, we would like to maintain what we call solar north pointing, so that every image you get from SDO without doing any data reduction is north, has the north rotation axis of the sun at the top of the image. And to do that, we actually have to kind of play around with the spacecraft attitude. And then we also need to maintain our communications with White Sands. And so here's a diagram that shows the complications that they have to cause. They have to rotate the spacecraft once in orbit, so it's always pointing at the sun. They have to keep the two high gain antennas, whose spots you can see hitting the Earth, going to White Sands. So it's a complicated mission to run, but we've done it well for 15 years, and we hope to continue it for as long as we get support. I was asked to show a hardware diagram, so here's one. I'm only going to show this one. EUV, which is what the telescope at the top here this telescope is measuring extreme ultraviolet radiation. In the case of EUV, you have very limited reflection options. Most of the time in the past, we've used glancing incidence telescopes, but they have very limited field of view and signal to noise. They came up with these really cool mirrors, which is, here's the primary mirror here, that are multi-layers of typically molybdenum and tin, stacked on top of each other, about 100 nanometers thick, and then they put one and then another and another. There'll be several hundred to 1,000 layers, and it's an interference process by this mirror and then also the secondary up here that allows them to reflect the extreme ultraviolet radiation. This is exactly what you see here in a Schmidt-Cassegrain telescope that you can buy from Meade or Celestron and a number of other venues. They have exactly the same components, a primary mirror that's curved and highly reflective, but we can't put a corrector plate inside of these telescopes because you can't get focusing out of these transmission optics. And so if you look at the equations that govern the AIA telescopes, they are exactly the same as the Schmidt-Cassegrain telescopes, but the tolerances are considerably higher. The output of the spacecraft consists of a whole bunch of images. We're at over 500 million images and counting, and that number has to go up every day. So we're really happy with the database that allows you to get any image that has been taken during the lifetime of SDO. Most of the images that you see are the ones taken in the EUV, and here we have these 7 here, and they're colored only to tell us which ones they are. These colors have nothing to do with the physical process. These colors just allow us to keep track of which one we're looking at. And then this sequence that you see here, I call the old man in the sun. And the idea is that you start here and you see the sunspots in a visible light image. Here you kind of see, and they look like eyes, and you kind of get more details around the eyes. And as you go up in these temperatures, you start seeing more and more filamentary structures. And so, he has a beard and stuff. And so these are really excellent for teaching kids what to look at in these images. The underlying thing that's causing all this is the magnetic field. And here's an image of the magnetic field where black means that the field is going into the sun and white means that the field is coming out of the sun. And you can see that there's a kind of a core surrounded by white. And down here where you see this filament lying along here, you can see that there's inwardly directed field and outwardly directed field. And then the Dopplergrams really don't look, one Dopplergram looks pretty much like all the others, but it's in their time series analysis that we learn a lot. And then it was really cool during the pandemic a couple years ago, we actually got a sequence of our images released as postage stamps. So I hope you bought a whole bunch of them. And the other thing that we get are these spectra from the EVE instrument, and now we see that the EUV is filled with spectral lines. Here's that 304 line where we saw the orange image at the beginning. We saw one of these 193 lines images a couple minutes ago. And so Eve sees the total amount of energy that the sun puts out in these wavelengths, and then that's what we can use to understand the Earth. So we have the total energy and we have where the energy came from, and that has allowed us to understand a lot of things about the sun that we were unaware of before. And here's a sequence that just shows how these images change over time as we go from solar minimum near the launch in May 2010 through solar maximum in 2014 and 15, and then back down to solar minimum in 2019 and then onward in 2020. SDO is unique to NASA missions because it has a 24/7 downlink and a high data transfer rate, a continuous high data transfer rate. The spacecraft and instruments are in great shape. We've been in orbit for 15 years. The Eve instrument has had some problems, but it's still producing really nice data. We are in our 4th extended mission right now. We've been moved to what they call a foundational science mission, so we don't do much research, or any research really, in our instrument teams. But we still produce plenty of data for the world community that uses SDO data. And in every 3 years, we have to write another senior review, and so the next one is due this year in August, and contributed to my desire to retire. So we are now over the maximum of solar cycle 25. We don't officially have the date of the maximum, but things are already starting to fade. Here's a sunspot from the visible light image. This is that HMI, orange HMI line I showed you in the spectrum. And here are what we call continuum grams or intensity grams. And you can see this big sunspots. There's a nice one there, a group of sunspots here, another group going off the edge here, and then you can also see white faculae up along the edge here that are the other ends of the magnetic field lines that come out of the sunspots. So the sunspot lines come out, go back into the faculae. The magnetic field causes the sunspot to be dark, but it causes the faculae to be bright. So it's one of the many fun things we get to study when we're looking at the sun. Now, this is what we got to look at from the sun for many years. We've been looking at sunspots for 400 years now, since Galileo took credit for work other people had already done, and published some sunspot drawings. We've been tracking them for now 425 years. So, but when we go to space, we get to see that under those over those sunspots, there's this whole wealth of other things happening that you wouldn't even get a clue of from looking at the sunspots. So all of a sudden now we see coronal holes, this area here, which is open field lines where the fast solar wind just pours out of these. These are like leaky faucets in the corona where the field doesn't arc over like this. So stuff coming up this field line is going to go and hit back onto the surface. These field lines essentially go to infinity, and so that's the fast solar wind. You've been probably seeing it'll replay in a minute. You can see this filament right here doing a liftoff. So we get to see those in exquisite detail and in many different temperatures as well. This is plasma that it's about 1 million Kelvin. Okay, what have we done with SEO? Well, let me just, I have to be a little bit of a philosopher now. It's very difficult to discover new things on the sun. We've been looking at the sun for 400 years. We've been looking at the sun from space for 75 years now. We kind of have, and the sun doesn't have any particularly permanent things. Every time we look at the sun, it's a little bit different. So you don't really get to be a discoverer in the sense that the people that did New Horizons, as they went by, flew by Pluto, They got to name things and discover things and find out there's ice plateaus and there's actually ice mountains and there's all kinds of cool stuff. So they got to find something that was new, they got to put a name on it, and become a discovery. We don't really get to do that anymore. Our job is to discover an understanding of what we see on the sun. And we've got some really cool stuff that we've been able to see, and we still are working on a complete understanding. First off are comets. You're astronomers, you probably got out there and looked at comets once or twice. They're really nice. They're kind of an oddball, an odd duck coming in from the outer solar system in this case. ISON was a new comet that came in and broke completely up during its perihelion. But there was another comet that we saw in 2012 that we saw actually in the EUV. And we had totally unexpected. We knew that comets were visible in X-rays, but we did not think that the cometary material would have a distinct life in the corona of the sun. We hadn't even planned for that possibility. I'm not going to show you the first one because it's really difficult to see. The next one was a Kreutz comet, and I think all of you saw it, right? Here it is, right here. You can see the tail of the comet as it spiffs through here over the course, that's about 30 minutes or so in time-lapse movies so that we get to see it all at once. You can see the loops of the sun over here. You can see the edge, the limb of the sun. And so this is well above the surface of the sun, and it's actually moving on and will go behind the sun from our point of view. And this is what's called a Kreutz sun-grazing comets. The SOHO spacecraft has discovered over 4,000 of these during its lifetime in space. And none of them had been seen to exit the sun. So we figured this one was going to go behind the sun and disappear like all the others. So we just repointed, while it was behind the sun, we repointed SDO to look square at the sun, and lo and behold, it came out from behind. And so this material up here actually lasts something on the order of 30 to 40 minutes. And we're able to track the magnetic field. You actually see the magnetic field lines or the vertical lines. So the material comes out, is deposited along a trajectory, and then very quickly turns and moves along the magnetic field line. That means it got ionized. It's not neutral material. It became ionized, and its gyro radius is taking it along, gyro motion moves it along the field line. This allowed us to come up with a relatively complete chemistry to explain this. Now, the details of all that are once again being thought of. We've only seen 2 of these. We've looked at 3 others, and they did not make it into where we could see the tail. But we're still waiting to see more of these to get a little bit more information about the emissions that we're seeing here. One of the earliest things that SDO saw was a solar flare. And everybody should say, wow, yeah, thanks. We've been seeing solar flares since the 30s, measuring them on H-alpha photograph plates since the 30s and 40s. But now we're looking at them in the EUV. This is a 3 different channels of AIA merged together into a single color image. You can see the flare, and after the flare, you see these loops that form. And those loops are called the late phase of the flare. And it turns out that only a small percentage, maybe 20% of flares have this late phase. But the amount of energy, even though you have this really big burst of energy from the X-rays coming out in the initial flare, the amount of energy that's emitted by the EUV in the EUV can be 30 to 100 times greater than the energy in the initial flare. So this has consequences for what happens at the Earth, and also for what the energy redistribution is as the flaring region returns to some more or less quiescent state. These tornadoes, or another thing that we see, this is in AIA 171, and it's particularly good for these. You can see they look like this thing, I believe this is the tornado here, and this is material that's moving around in the magnetic field that is coming out of the surface here. And it's not really a tornado. You're probably much more familiar with tornadoes in Texas than I am here in Maryland, but tornadoes are a thermal inversion that goes crazy. These are magnetic field lines that have just little blobs of plasma moving around in them. And they look like a tornado, and so it kind of got stuck, but they are not actually a tornado. And then one of the cooler things is coronal rain. And so you watch this and you say, well, there's some loops right here that form, just like they did after that flare, but we think the material is coming from above. And it's falling down onto these loops and getting heated and then glowing. And in this case, glowing to saturate the detector. And then once it gets hot, it's the reason you see it glowing is because it's cooling down. And then as it cools down, it then falls out and comes down onto the surface as this coronal rain. So it's a very nice, compact loop structure here that shows that phenomenon. And just to show you that here's the Earth over here, which you could just fly right through. Be a great view. Get EUV eyes. Now I'm going to show you one cool thing about having the telescope on 24/7. Here we have a flare over here on the right limb, right over here, the receding limb. We have a flare. It's a X2, I think, flare. And if you stop looking at the flare and look at the rest of the sun, you see that things happen across the sun. That the flare happens and things are, there's flickering happening. Part of that is observational. But there's something you can see kind of ghosts going across, especially in this area. The flare goes off and you can see it gets a little darker right there. And so if you take a sequence of images and then subtract, do a running subtraction, so you take image 2 minus image 1 and image 3 minus image 2, a running difference, do that in 3 wavelengths, and once again, build one of these 3 color images and then make a movie out of them, you get this. So there's the flare. And now you can see, indeed, that things from that flare go all the way, you can track things all the way across the sun. And it causes something over here to happen. You can watch along the limb, you can see these magnetic field lines reacting to the presence of whatever the flare sent over. You can see the magnetic field lines are bent over a little bit as this wave propagates around. Now this movie spans about 1.5 hours, and so some of the faster waves are moving at 400 kilometers a second as they go across the sun. So there's an opportunity to study plasma physics in a really in a really nice way, because this is all a result of the energy being put into plasma that then has to move along the magnetic field line. So it can't freely expand as it tries to do something. It's restricted to moving along the magnetic field lines. And so you get all these, the helmet streamers light up, the loops light up, simply because this extra material comes along and it has a strong field, so it moves along the field rather than continuing straight. This sequence has been well studied by our scientists, and it's one of the best examples we have now of really global connections of the sun. Looking at the helioseismology data, we would like to look inside the sun. Yes, it's cool to look at the sun and all the flares and all that stuff. But what we really want to know is, are there horse latitudes on the sun? We want to know what motions are taking place inside the sun and how do they cause what we see as the sunspot cycle. Because it appears that it's the motions inside the sun that move the magnetic field around on the surface. And in many cases, the biggest thing we notice is that it takes field towards the pole. So here, this is the velocity towards the pole, and that's about 15 meters a second, going, or about 35 miles an hour. And that just moves stuff from here, where the active regions are, about 30 degrees, and it takes the field from the active regions and moves half of it up here, and it moves the other side of the field downward in a more complicated process, downward towards the equator. So we get a separation of outward and inward field by the actions of these motions inside the sun. And we think this is where the solar dynamo comes from, and this isn't new. The dynamo, we've understood the dynamo is due to these internal patterns of velocity or circulation patterns. We would recognize these as the jet stream, which is the result of the interaction of some meridional velocity cells here on the Earth. The way that weather moves across the United States is a similar pattern to this. So it's just hydrodynamics, and we think we're starting to understand it. And HMI has been the premier data set for understanding this, and whether the stuff goes up, goes down, and comes back, and kind of cycles around, looking like a kidney swimming pool, or in this case, it goes up and it has it coming back down here, and it has underneath that another cell where it goes up, probably comes down here. So we're seeing it's getting more complicated as we get better data. I'll skip that. The magnetic field is the source of all solar activity. It has been said that if it wasn't for the magnetic field, the sun would be as boring as every other star. And so the magnetic field is why the sun has sunspots, and the magnetic field is why the sun has such time-dependent effect on the Earth's atmosphere as we see it having. So here, I'm going to show you essentially day-by-day maps of the solar magnetic field from near the launch of SDO, it's actually late in 2010, up through 2022, I think. I've been trying to get it to go forward, but I retired and lost my data analysis computer. So I have to try and learn Python. And so here it goes. Now you can see the date. This is the day. It's called the Carrington rotation number, but that's essentially a day counter on the sun. It's one rotation of the sun. You can see the date, so we're moving up into solar maximum, and you can see that the active regions are forming around 30. This is 30 degrees right here. This is the sign of 30 degrees. And you can see that the active regions come in. They all stick down here in the very low latitudes, but you can see the field streaming up towards the pole above. So you can see, and you see these waves of field of black and white, so inward and outward field moving towards the pole. And over time, that changes the polar field. And I'm not sure this movie is showing well enough to demonstrate that. There's a couple things you can see right away from this. Here is the early sun. This is somewhat in the rise of solar cycle 24 back near the beginning of the mission in 2011. And you can see that the black, the inwardly directed field is in front of, it's to the right of, the white outwardly directed field. And here is an image from solar minimum of between 24 and 25, and you can see it's the opposite. So there's white outwardly directed field leading the dark inwardly directed field. And this is one of the things we've noticed. This is one of the confusions about the sun. It actually takes 22 years for the field to go with the outward field leading in the north to the inward field leading in the north back to the outward. That takes 22 years, whereas it only takes 11 years to just do sunspot number, which is a measurement of the field, but not a very, doesn't have a sign. And let's do a little physics. Here is cycle 24, the entirety of solar cycle 24. I just took those day maps that you saw and just did an average of all of them from solar cycle 24. The thing that you should notice is that there's a lot of structure to it here, but up in the polar regions, very flat, very kind of bland. But here, the first, up through June of last year, you can still see that there's a certainly outwardly directed field in the north and some hint of inwardly directed field in the south. And this is the other half of the solar cycle. All these sunspots and everything, that's just the sun trying to get rid of the field. And the effect at the poles is what I study to see whether I can predict what the sunspot number will be in 5 more years. Yeah, let's skip that. I want to do, so here's my personal research. We look at the poles here in many different ways. I think my students are very tired of the fact that we study the poles. And you can see that there's a polar hole right there. You can see another one right here. You can see they're very difficult to see because the sun has rolled over. The sphere of the sun rolls over and it's hard to see what's happening at the rotation poles. Here is at solar maximum. You can see that the pole is very uniformly lit up, showing that there's probably no coronal hole there. And then once again, we're back to solar minimum and a very well-developed coronal hole has appeared. And here is the field at minimum. It's hard to see any, there's very few things. It's mostly salt and pepper across the disk. Here are the sunspots with the field that's moving towards the pole. And then there's just, I drew these to help show that. Okay, somebody called me up and they said, we were already through solar maximum 25. This was in June of 2023. And they had seen this erupting filament taking place. So I got on and made this movie, and this just shows that we're entering the maximum of solar cycle 25, and the field is still up here from the last cycle, and this, what is called a polar crown filament, is the last thing, the last defense against magnetic fields on the sun. And it is basically taking that field, new field from below, from the down in the equator in mid-latitudes, is moving up, and it has an oppositely signed field join, and you form these really cool looking filaments, and then it takes off and it removes some of the field that's inside the filament. It destroys some of the new field that's coming up as well, but the important thing is it's getting rid of the field that's at the top, setting the stage for the next cycle to appear. Now, this is one of my high school students went through and took the spectrum and sonified it using a piano voice. And you may listen to this and say, this is really nice. But on the other hand, if you ever listen to a Bach piano variation, variations, the Goldberg variation. There's a lot of it that sounds just like this. And a human has to play those. And we did this for mini synthesizer. But you can hear all the lines that are in the spectrum. And it's pretty neat to hear that and emphasize these how small these are, how short-lived the lines are in the music. SDO has seen some other things. We have seen one Venus transit. The next one will be 128 years, roughly speaking, from 2012. So we probably will not be around for that. We do get to see more frequent Mercury transit. Here's a really nice one in 2019 when Mercury was near its perihelion, which means it moves pretty fast. And so you can see wide spacing in these dots. And in here in 2016, it was near its aphelion, or furthest from the sun. And these dots are the same timing as the dots in 2016, but you can see that Mercury was moving considerably slower. The next Mercury transit is in 2032, and we really hope SDO will continue until then. You can get a lot of information about SDO. We give our data away for free. We have an open data policy. Many of the pictures that I showed you tonight, I created using the archive at sdo.gsfc.nasa.gov. If you want to do a little bit more image processing, we encourage you to go to helioviewer.org, and you can actually manipulate images and merge them on top of each other. You can make your own 3-color images and stuff like that. So here's my favorite thing that ever happened on SDO. I call it the Trebuchet eruption. And I just love to look at it and see how complicated the motion is in the solar magnetic field as it attempts to throw off some magnetic field and some plasma, and some of it can't go and gets bound, continues to be bound to the sun, but it never falls straight back onto the sun. It always falls at an angle. So thank you very much.
Brilliant. Does anybody have any questions? Got it.
What is the process that generates the sun's magnetic field?
So that's one of the problems. We think we know what it is. You have to get a magnetic field here on the Earth. You typically move electrons around, and so you have to. That's what ferromagnet has, aligned electrons in the orbits of the iron or whatever the ferromagnetic material is that you're looking at. A coil of wire, if you pass a current through it, will create a magnetic field. So it's the motion of charged particles. In the sun, we have electrons, but we also have ions, and they're kind of more stuck together to each other. So it's some kind of taking that plasma and moving it around and just having a relatively minor separation of the charge that allows, it's actually not, it's the motion of the charged plasma that creates the magnetic field. It takes place deep inside the sun, and then as it comes up through the surface, towards the surface, it gets amplified. It also, because the convection zone is quite chaotic and the motions are not as smooth and laminar as it would appear from our meridional flow calculations, it gets twisted up. And by the twisting magnetic field means that it gets stronger. It either reconnects and goes away, or it stays as magnetic field and increases its strength. It gets stretched out, and once again, it either has to break and reconnect, or it gets stronger because as I pull it apart, it has to be able, it wants to bring itself back together again. So it's called the solar dynamo. It is the motion of the charged particles inside the sun. And what we are seeing at the surface of the sun is the eruption of that field out into the universe, pretty much as it's the sun getting rid of its magnetic field. It's already been generated. We can see evidence of how it works by looking at sunspots. You often see sunspots as pairs, and one of them typically has more outwardly directed flux and the other has inwardly directed flux. And you can see that you can almost imagine the magnetic field coming up through the surface, going up out of the surface, and then coming back down through the surface. So it's the motions of the charged particles within the sun that generates the magnetic field.
What exactly were the factors in deciding to put SDO in Earth's orbit instead of orbit around the sun close to the Earth?
So there's only actually a couple of orbits that are usable in space. You would think that space is pretty big and there'd be an infinite number of orbits, but there's only a few that have what we in the science community would say have good qualities. The SOHO spacecraft, which in many ways was led up to SDO, so it launched in '95. And it went to L1. So it sat comfortably between the Earth and the sun, about a million miles from the Earth. And so it looked at the sun without any obstructions. The problem is, it's a million miles from the Earth. And the Earth rotates. So you don't have radio communications with the spacecraft unless you have around the world radio antennas. And everybody wants to use those around the world radio antennas, so you don't get them as often as you would like. So as the mission aged, we tended to store data on the spacecraft and send it down, every 6 hours, every 8 hours, you would get a burst of data down from the satellite. Well, they looked at that and said they would rather get more data, a higher volume of data, so that we can get higher resolution images. The images on SOHO were 1K by 1K CCD images. The EUV images, actually the EUV and visible images, the HMI images on SDO are 4K by 4K. So there's 16 times more pixels that you have to send down. You got an image every half hour or so, every 15 minutes from SOHO. We get an image every 12 seconds in each of the AIA channels, and we get an image every 3 seconds in HMI. So we get far more images down to the ground to examine things. So our time limit is 12 minutes instead of a half an hour, and a lot of things happen between 12 seconds and a half an hour. And finally, the HMI data, you take a bunch of images at different positions in the spectral line that we're looking at, and then you have to combine them to get the Dopplergrams and the intensitograms. And if you launch a spacecraft, the only thing you know is the software is out of date. And so they launched SOHO, and they had limited capability to fix things on orbit. And by doing it the way we did it with SDO, you bring all the data down and you can combine them many different ways until you find the optimum solution. So even today, we are thinking about whether we need to change how we do the data reduction. And if we find a better way, we can go back to the beginning of the mission and reprocess all the data and improve it and get an improved data product. So it really was the communications with the spacecraft that put us into a geosynchronous orbit.
Thank you. Anyone else?
Do you guys compare data with the Parker Solar Probe?
Flying through.
Parker is essentially an in situ set of instrumentations. We act as the magnetic field from SDO and some of the coronal measurements as well. But Parker has a problem. It sees stuff and it wants to know where that comes from on the sun. And there's no signposts on the sun. There's no real position information where things come from. And so SDO, and in particular the SDO magnetic field measurements, have been a crucial part of understanding the particle data from the Solar Parker probe.
Anyone else? Are there any questions online? All right, I'm going to take that as a no. Listen, Dean, thank you for your time. There's actually quite a few solar buffs in this club, myself included, and this has been absolutely fascinating.
Okay, well, thank you very much. When I do the astronomy for people who sleep at night talk, I often have a set of solar observations that people can do. I decided not to put that in here. I thought you all would have that, but I encourage you to get the H-alpha telescope or a calcium K telescope. You can see a lot of this near surface structure in H-alpha. Well, what you don't get from H-alpha is the coronal loops that are so easily seen in the EUV. But we combine data from many different observatories with SDO. I was in Japan a couple months ago, and I went to a solar observatory, and they were trying to look at a sunspot, and they had the SDO image next to their image. So they're using SDO to point their ground-based telescope. And I thought that was really nice.
Nice. Well, thank you very much, sir.
All right, well, keep looking up.
You're welcome to stick around if you want. And we want to take maybe a 10-minute break.
Oh, I think I will be going now.
Okay.
Well, thanks for letting me come and give a talk.
Thank you, Dean.
All right, bye.
Watch your eyes.
Okay, yeah, do it.
my minimum, it's right at my minimum confidence temperature, right here. Made it. I didn't know this. But if I stand right here, my minimum confidence. Stephanie will come in my office during the winter time. It was a little floor heater and stuff. She'll come in my office and she'll stand there and just look at me. And I'm like, hey, what's going on? She's like, oh, no, this has, I'm warming up my legs. This has nothing to do with you. It's like, okay. As long as that feet ain't on me. I'm watching YouTube on Newflex. That's how boring it is. This year's Navy. Just like a walk around. Yeah, probably just going to get turnkey. The map supports 320 pounds. To say that it might be over-engineered. Christian, let me know when you're ready. Well, then they can just listen. Right now, we're going to talk about what's going on in the sky for the next month. And there's a lot. There's a bunch of stuff going on. So my little feature cover picture here, if you want to go to the next slide, is Michael Monroe's picture. This is what a sound to noise ratio does for you in dark skies.
And this is the Milky Way in the Big Bend park. Just, I imagine, I mean, I've been down to Chile where it's a similar, I mean, it's portal -10, you know, it's just, it's like looking up and you're just like, it's like a magazine centerfold, astronomy magazine centerfold up in the sky. Next slide. It's sexy, so, you know, whatever. Okay, so I'm going to keep this slide on here until the thing blows up, okay? We've actually been talking about this since January of last year, and it'll blow up, and we'll mention it then, and we'll promptly forget about it because it'll probably be the return of Halley's Comet at that point will take over all the news. Next slide. It's galaxy season, so we're looking at space opposite of the core of our own Milky Way galaxy. And so we're looking through the thinnest part of the galaxy. There's a better contrast with the night sky because there aren't so many stars in the way. Sean Paul actually got this as a picture of the Leo triplet back here in the back. So next slide. Bright comets. So I didn't think I was going to be talking about comets until probably about November, when we're expecting to see some possibly bright comets. But thank you to Bruce for pointing it out. There's a comet, 2025 F2, discovered by the, actually it was discovered by some people that were looking through the SWAN data and found it. I think that's the case. Yeah. It's in Andromeda right now. It's dimming, and it is a morning comet. And there isn't a whole lot of time left to see it in the morning if you want to, but you might want to check that out. This is actually my picture. It's of 103P Hartley that I took last year, I think. Next slide. Occultations and close approaches. So for all you that like this sort of stuff, this one's actually a pretty cool one. Mercury and Neptune are going to be just a little more than half a degree apart. And Saturn and Venus are going to be within 4 to 5 degrees. So there'll be this nice little cool bunching. So all your non-astronomy friends that text you and say, hey, what's all this about the planets aligning and stuff? You'll be like, well, here we go. When the media was talking about it, it was actually spread across the sky. Here's actually closer to an actual alignment. So next slide. By the way, that was Stan Hobson's picture of the moon, and that little dot, if you can go back, that little dot right there is Neptune. It's last year's moon and Neptune conjunction. Next slide. So Mercury is at greatest western elongation on the 21st of April. This year it really isn't showing as a really good elevation year for Mercury's elongations, but it's in the morning. It's morning star again. So there you go. Next slide. The Lyrids meteor shower. You know, we have a little dry spell, a couple of months with no real meteor showers. So the Lyrids come back. It's Comet 1861 G1. Gives us a meteor shower. It peaks on Wednesday, April 23rd, in the early morning. And it's estimated in between like 18 and 20 per hour at zenith. It's a waning crescent moon, so it's pretty favorable. Next slide. New moon is Sunday, April 27th. This is Glenn Fraser's work with crescent moon. Next slide. Asteroid 4. This is Vesta. This is the 4th asteroid that was discovered. It's the second largest one in the asteroid belt. It'll be at opposition on Friday, May 2nd, and it'll be just naked eye in the dark sky. And more on this in a second. Next slide. And then we've got the Eta Aquarids meteor shower. Mama is the aforementioned Halley's Comet, and this one is peaking Tuesday night, May 6th. It goes into Wednesday morning, the 7th. There's an estimated rate of 30 to 60 an hour. The downside of this is that we're into a 10-day waxing gibbous, so it'll be bright, and you won't be able to do but catch the brighter meteors, but it's still a good meteor shower. Next slide. Okay, so asteroid number 9. This is Metis, not to be confused with Metis, which is the Jupiter moon. And I looked this up, I was like, okay, so how many moons are also common with names of asteroids? And Jupiter's moons. There's apparently 13 of Jupiter's moons that with asteroids also share the same name. So, fun fact. Metis is going to be in Libra here. Vesta is actually pretty close to it. So if you got yourself a little wide shot right there, you'll be able to see both of those asteroids in the same space in the sky there. Next slide. The full moon in May is on Monday the 12th. And this is Patrick McMahon's partially eclipsed picture there. Next slide. Okay, and so because it's galaxy season, all these constellations that are in the sky right now are just packed with galaxies. Because that's what we're looking out at, is from, outwards into, from the Milky Way. This is Canis Venatici, and I call it Canis Venatici, but that's what all the internets say we're supposed to say. The hunting dogs. This was one of the 12 or 13 constellations that Johannes Hevelius came up with in 1687, amongst things like Leo Minor, which I featured last month, Lacerta, Scutum, Sextans, Vulpecula, and there's 4 stars with known planets, 5 formally named stars. It's not a very bright constellation as far as the stars are concerned, but it is really full of a lot of visual treats. By the way, in the dogs, I didn't know that the dogs had names. This one is Chara. This one is Asterion. So there you go. Now you know. Next slide. And they're Boetis's dogs. Boetis the herdsman. You need dogs for that, I guess. So Messier 3. So this is a beautiful globular cluster in this constellation. It was actually the first object, Messier 3. It's the first object to actually be discovered by Messier. So, one, the crab, the Chinese discovered the crab, I guess, but, and then 2, whatever 2 is, was discovered by somebody else, apparently. So, it's about 500,000 stars, at least 500,000 stars. Next slide. Down here at the bottom here. This is Stephen Kennedy's really good shot of this. And it's actually got the largest variable star population of all known globular clusters. And it's got a higher metallicity than the average globular, which means that the stars are older, there's heavier elements in the stars. And I'm sure you'll be talking about metallicity in a few of these other slides as well. Next slide. The Whale Galaxy. It's also known as ARP 281, and you'll understand why. When you see it, it is an edge-on spiral galaxy. When you look at it, you don't know that. There's a lot of starburst formation going on. And there's actually been so much starburst formation going on. The stars, they're hot, they're supermassive, they burn extremely hot, which means that they burn blue in the spectrum, and they go supernova, and they've had so many supernovas, actually never been one that's seen in here, but they know from the remnants. There's been so many supernovas that it's created what they call a superwind that's actually blowing gas out from the disk of the galaxy. Next slide. This is David Koch's picture of the Whale Galaxy, and yeah, that's an edge-on spiral, believe it or not. Next slide. Then we got an SEA 106. This is one of the largest and brightest of the galaxies near to us. It's similar in size and luminosity to the Andromeda Galaxy. It's also an important galaxy because the Cepheid variables, which are used as a distance yardstick, as a measuring standard for astronomical distance measurement, those are of a similar metallicity to the Milky Way. And the important thing about that is that because the metallicities are the same with the Cepheid variables in the Milky Way, that they're able to use, they're able to make accurate measurements with our distance to Messier 106. Yes? Standard candle, that was the phrase I was looking for, thank you. I was dancing around that with every other phrase. It's the standard candle. So there are other Cepheids with different metallicities, but this galaxy, with its similar metallicities to the ones here in our galaxy, actually helped us get more accurate distances. Next slide. And this is Bob Circus's lovely picture of Messier 106. Next slide. All right, New General Catalog 4618 and 4625. So this is a gravitationally engaged pair of galaxies. It's an odd set because both galaxies, next slide, they're spiral galaxies with one arm, and it's both of them. Isn't that crazy? So that's odd. They speculate that this is because of possible, past. They just goofed each other up. That's what's going on there. Something you'll see very, very faintly here is a bigger spiral here. So these arms actually go out, and they didn't discover this until later because they saw it through UV. So seeing the galaxy in ultraviolet light actually made these arms stand out. You see this right here, that this one, appears bigger than this one if you don't see those arms, and it's like, 4 by 3 minutes. And over here, the parent size of this is 5 by 4. It's a much bigger galaxy, but it's because of those faint arms there. Next slide. Whirlpool Galaxy. This is known as Messier 51. Maybe you've heard of it. Also ARP 85. And so beautiful grand design spiral face-on with us. It's doing a gravitational interaction with M51b, which is a smaller dwarf galaxy. And it's bright. I mean, if you guys haven't seen it, anybody that hasn't seen it in a telescope, usually an 8-inch or bigger telescope in dark skies, you can see spiral structure in the eyepiece. It's really great. Next slide. And this is my picture of it. Next slide. Messier 94. So this is also known as the Croxi Galaxy. It's a face-on spiral. It's got a large outer ring structure that's outside of the spiral arms. It's really more of an extension of the spiral arms. It's got an inner spiral. It's got an inner ring that is actually a starburst formation area that's circling around the middle of the core, just outside the core. Next slide. So this is David Cox. Really good picture of it. There's that outer ring. And there's the inner ring with that starburst formation going on. Next slide. It's a really good picture. So more about this, a full listing, and you'll see the numbers here. 511 deep sky objects. It's a very object-rich constellation. And so these are the sites that I researched to get this. And one of them I came across is, it's an acronym. I probably always pronounce that as NOIRLab, but it's noirlab.edu is an amazing site for information about deep sky objects. Next slide. So this is the latest picture that came up. This is from Kristen Carlson. Is she here? This is an amazing picture. So this is the re-entry, or no, this is a rocket separation of a stage by a SpaceX rocket that she captured in her backyard. Pretty cool. So thank you very much. Do we want to keep the lights off for the rest of it, or? All right. What do we have next? The business meeting. So we're doing stuff a little different tonight with the business meeting before the monthly reports.
Thanks. So the executive board had a meeting last week. Notice the resemblance? No. And we had a couple of things that we wanted to point out, but I see first up is the financial report. So, Constantine, come up and give us a report.
Thank you, Bruce. As you can see on the report, it's been a fairly quiet month, except for a couple of donations, 1550, and also our income from our star party, our first star party for the year from the foundation. Expenses very minimal, routine expenses, software, that kind of thing. And income primarily from our 11 new members for the month of March, and so far this month we've had 2 new members. The bottom half talks about where we are with regards to Rising Star, and you can see the income from the Star Party and the income from the donation. We're sitting at $74.89. We do have a payment coming up this month and some interest, and we'll be able to talk more about that at our next meeting. But it's obvious that we should be able to make a payment a little bit higher than just the minimum required. Any questions? Thank you.
Thank you. So one of the items we covered at our special meeting this past week is an automation project associated with the Noble Observatory. What we've heard is that there's some additional equipment that needs to be purchased to make this observatory fully automated. So Bob has a presentation to bring to us tonight with the understanding that we're looking to vote on that, vote for the funds to move forward on this project. So Bob?
Thank you, Bruce. Good evening, everybody. I'm waiting for Kristen to work his magic over here. Okay. So I'm back again talking about the Noble. I'm going to be talking about it a lot until we get it finished. And with the support of the board, Jim, Catherine, and I, Jim actually gave the presentation. I was out of town. Can you go to the very first slide deck? Okay, so this is what we're here to talk about. is the Noble Observatory Automation Project. Right now, we can image from the Noble. We can do live streaming from the Noble. And we can do it remotely from the Noble. But we really can't because we can't rotate the dome and we can't lift up the shutter or close the shutter. The principal issues with the shutter itself. Next slide, please. So I'm going to talk about how we got to where we are. We have two domes out at Rising Star. The first dome that's fully functional is the MOB. It's Jim McCatherine's observatory. And we spent a bit of time putting it together. Jim is an architect. He is an astronomical architect as well as a terrestrial architect. So he put a lot of time and effort into the design and sometimes listened to me about how we should do the software and some other stuff. So what we did when we built this is it was designed for Jim, but we wanted to take lessons learned from this construction. So it's been operational since last October. Jim has produced some pretty cool images. I even got to play with it, and so it's an awesome thing. And if you've ever been out there when it opens up, you sure know when it opens up. Boy, it wakes up the dead. So is it remote operable? Yes. And so these are design features that are implemented or will be implemented in the Noble Observatory. Remote access. That means we can run these observatories from anywhere on the planet, and I'm presuming the International Space Station if we have network connectivity to the planet. We've developed remote operations procedures for the McCatherine Observatory, which we're playing into the Noble, and we have automation opening and closing the dome, running the telescope, and we running pretty much the same software, and we have a lot of lessons learned from this, of which, if you're not a moonlight focuser person, you really need to be. So that has to do with my 127. So this is what it looks like, a working, functioning observatory at night. Next slide, please. So a little history of the Noble Observatory. It is named after our founder, Charlie Mary Noble. Sean Paul has agreed graciously to build and design a placard. All I'm going to do is provide him information, so we'll have something outside of the Noble Observatory. Construction started February 17th of 24 with our electrical and rough out work. These are all the dates. And the key dates, the image train was installed earlier this month, and we're starting the automation work. Let's see here. We had I don't know what that FWAS opening, that's supposed to be the 25th of 2025. So what's going to happen next month is there's going to be some training sessions and that kind of jazz, even though the automation is completed. And we hope to have everything done, pending the group's approval, by the new week of July. Next slide, please. So what's the image train? There's a lot of stuff here. Our observatory is a 2.2 meter next dome. It was graciously gifted to us by one of our members. That's the image train there. It's a Raza 8 with a 183 MC on it, and a high-performance pier donated by telescopepiers.com. The mount was donated to us. It's a CEM60. It's a fantastic mount. It is awesome. It's a beast. We have presently an Mealy 3 fanless computer on it. We're going to run Nina, PhD2, Sharp Cap, Stellarium, and a couple other bits and bobs that are not yet there. We have an internet camera inside the dome. It's always on, so we always know what's going on inside the dome. It's digital and infrared. We're going to have the flat panels are on order. I have the dust cover at home. The flat panels should arrive in a week or two. And that flat panels is to do two things: to cover the RASA when we're not using it, and when we need to create flats and other calibration frames, we'll be able to do that. What you can't see on the bottom is we have a weather station on weatherunderground.com. It's not working yet. You can find it. You won't see any data yet, but when we get our weather stations set up, it'll be updated regularly. Next slide, please. So here's the current state. Remote operations are available now. If you have someone to rotate the dome 15 degrees every hour. It's polar aligned within 1 arc second of NCP. Guiding is between, the max guiding we've seen is 0.12 RMS. It's been as low as 0.6, 0.06. It's usable. The dome has to be manually operated, as I mentioned before. And we're in the process, there's a small group of about 8 folks. We're creating operational procedures, which include network and computer access, software access, physical access and monitoring, scheduling, that's going to be hopefully a big deal, data storage and access, and training. So over here on the left, this is, if you're looking, if you want to see what's going on inside the dome, this is the camera inside the dome. So, and it's recording 24/7, and it rotates up and down, left and right, so we can swing around and see what's going on. We have a digital logger out there. All that means is that we can turn off and turn on equipment remotely, like the computer, the mount, cameras, and that kind of jazz. And this is just an example of what NEMA looks like. Next slide, please. Okay, so what do we need to automate, and why do we need to automate? So what we need is the ability to open and close the dome remotely. We need to be able to synchronize the dome rotation with the mount. We need to be able to close the dome, and what that means is the shutter. We need to be able to close the shutter when we detect inclement weather, a loss of power, lost communications, so that we can make the dome safe. And then we'll need a weather station to monitor local conditions. The outputs from the weather station will let us know when clouds come in, the dew gets too high, the wind is too high. If it starts raining, we can protect our investment out there. Next slide, please. Okay, so utilization, how is it going to be used? Our hope, my hope, this is my personal hope, that as many people in the club that want to use the Noble can, whether you're doing imaging or remote astronomy. So NINA is for imaging, SharpCap is for remote astronomy. That'll allow you to record and film objects in the sky and show it to your friends. And I envision that we'll be using remote astronomy when we're doing star parties, stuff like that. So we want to make it available to as anybody that wants to. The objective there will be, as part of our operations and training, if you want to be able to image, we'll train you up on how to image. And there'll be a process for you to learn and then demonstrate, and we check you off, and then you can schedule time. Same thing for live streaming. Okay. Only in this will, as far as actually operating, it will only be available to club members. And then we want to maximize the use of this asset. The only real constraint, once it's automated, is going to be weather. So imagine, we get one good night in the last 14, we can do something, and you don't have to drive 2 hours out, 2 hours back. You can do it from the comfort of your home. Next slide, please. Okay, here's the meat and potatoes of it all. What do we need and how much is it going to cost? So what we need, I'm going to just a weather station, and we've done a lot of research on this. So the best weather station for our purposes is something called Skylar E from Interactive Astronomy. It's $995, and anybody that's out at Rising Star can use that weather station to enable or disable their image train if the weather goes bad. So, for example, the Jim's Observatory in the Noble can do that. Bill likes to bring a tent out to protect his image, his trains from the wind. So if the wind kicks off, he may not be able to close his tent, but he can get alarms saying the wind is crazy or it's going to rain, and then he'd be able to deal with that, for example. Our dome is from a company called Next Dome. They're based in Canada. And we have the version 1, kind of an early version of the version 1 shutter controller, and it really doesn't work very well. It's honestly, it's just not designed very well. So we have tried to see if we can use it, and it's simple, we can't. Basically, what that thing does is it'll open and close, and then when it gets to 50%, whatever, if it's open or closed, that's it. It will not do anything until it gets charged up again. And there's no way to charge it up unless you're physically there. So that's an issue for us. Then the rotation kit that came with the dome, it'll work again, but it's not as efficient as we want it. A lot of folks here have probably seen like the gear that it's used to run the track. It is very rough, and we think it's actually going to cause damage sooner than later. So we want to replace that with a new rotation kit and shutter kit, and all of that is going to be about $4,300 for the weather station and the automation kit. We do have one shipping charge, and that's going to be from Next Dome. It's $290. A member generously donated a pretty sophisticated security system. That's up there because we're going to install at least 1 or 2 cameras out there. And we have miscellaneous. I did the math, that's 667, that's for stuff that we've forgotten. Like we want to put mats down on the floor, we need to seal some stuff up, that kind of jazz. So our not to exceed amount is $5,000, and hopefully it's going to be a lot less than that. We've already raised $4,500 for this project from anonymous donors. And so our next steps, we've already gotten board approval. They've asked all kinds of questions. And the next step is to ask membership to approve the project. Next slide, please. Any questions? Okay. So tariffs are a big thing right now. Just a couple thoughts because some of the board has asked about them. I've learned more about tariffs in the last 3 or 4 days. It's kind of like Worcestershire sauce, right? I make chili. I think it's pretty good. But some of our friends are vegans, so when you make vegan chili, you think, I'll throw Worcestershire sauce in there. Well, you really can't, because I've gone all my life not knowing this. It's got anchovies in it. So they actually make a vegan Worcestershire sauce. So the point I'm trying to make is I've had to learn more about tariffs than I ever thought I'd have to learn. So most astronomy companies are eating the cost of tariffs, because contracts of, like, from High Point and Gina and other companies that we do business when we buy equipment from them, they're not allowed to adjust the price. The price is the price. So this is important. Tariffs on imports from Canada have been deferred for up to 90 days. So we want to get our order in as quickly as possible. Tariffs are applied after all taxes are paid or calculated. On the next dome equipment, there is no taxes, so that's good for us. One thing I learned through all this exercise is that imports from China are subject to tariffs, but not all of China. Hong Kong is accepted. And why is that a big deal? Because if you buy stuff from, like, Wander or Astro for your automated flip flaps, no tariffs. So that's a good thing. So at the moment, we don't expect to have to pay any tariffs. If we do, it'll either be 10 or 25%. I've talked to a guy named Dan who runs worldoftelescopes.com, and he's doing some checking for me. So I hopefully have an answer this week. Any questions about this? See, I'm just managing tariffs by fact, and that's it. Okay, next slide, please. Okay, so proposed schedule. The goal is to have this done hopefully towards the end of July. And these dates are Sundays, Sunday date, weekend and Sunday. So this is what the schedule looks like. If approved, we'll order our equipment pretty quickly. And we're working on operations procedures. And I'm actually going out this weekend to do some stuff that I can do now, like get floor mats in, or measure for floor mats, or get prepared for adding equipment out there, that kind of thing. Okay. I reckon between now and the end of, by the first Sunday in May, to get the weather station installed, up and running, test our operations procedures, and install the automated flat panels. At this point, we can run, we'll have our safety stuff in, and we'll be able to run everything remotely, get synced up, and be ready to go from that perspective. Then by the 11th, we'll continue our operations procedures development and possible training preview. And we'll give a pretty detailed report to the board. And then the 25th is that week we will present, Jim and I will be presenting to the club, as Bill mentioned earlier. And, excuse me, 6/1, that's Memorial Day weekend. That's after. This is Memorial Day weekend here. Okay? But this is after. That's a Sunday reporting day. On that weekend, we hope to have our initial training out at Rising Star on the Noble. Because we want you to come out, we want to show it off. I mean, it's really great to talk about it, but to get out to see it and have a look and watch it operate, I think is really cool. So, and our schedule is subject to change. As I mentioned before, the next dome equipment is a 10-week lead time. So, next slide, please. So, starting next month, as part of Bill's What's in the Sky, we want to present a few objects. We want everybody to vote on what to image from a club perspective. This month, if the clouds ever clear, we'll attempt to do all 5 of these. Now, we think we can do all 5 because it's a RASA, and a RASA is really, really fast. So we don't have to get, and we're shooting one-shot color, so we don't have to take gobs and gobs of hours of images to be able to process this. So I think this is probably a good order, M106, M51, M63, M94, and M3. And they all frame very well with the way the camera is installed on the RASA. So I don't want to take up too much of everybody's time here. Next slide, please. Any questions? That's scary. Okay, well, thank you for your support.
Thank you. Catch lights. Sorry about that. I forgot the health warning about turning the lights on in a dark room. All right, so let's go to my slide. No, go back. That's it. So, as Bob was saying, Jim and Catherine presented a very similar description of the modifications to the Noble Observatory at the executive board meeting, and the board voted to to make a motion here at tonight's meeting to authorize the expenditure of $5,000 towards this project, where $4,500 of that is from anonymous donations, and then the club would fill in the gap of the $500. So the club would be on the hook to spend $500. And then the other part of that is no equipment would be ordered sooner than fully funded by the anonymous donations. That means we would have the cash in hand to move forward. That was the motion that the board made. And so I'm bringing that motion up to the club right now, because we have 31 members here to discuss and approve the proposal. How many people do we have online? 13 currently. Help me with math. We're what? We're shooting for 44? No, that we have 44. And how many members do we have? 230? 20% of that is 46. So we're short by 2. So we don't have a quorum, so that's an issue. I don't know. Well, maybe. So we're stuck. Maybe it's a conditional vote. If it passes, then and we don't need the quorum, it goes forward. If we do need the quorum, then we're stuck. We'll have to come back. So, I'm sorry? We could. If need be, yes. If we don't get it here, we'll look at other options. It won't be a month later. It'll be later this week. So one thing that I noticed in Bob's presentation, that if the funds were allocated, he would start ordering tomorrow, but the board didn't want to move quickly until we had all the donations in place. So that's a problem. So we have a problem here. But the proposal that I wanted, the executive board meeting that I wanted to bring to your attention was this one, and then we would move from there. through discussions and questions and perhaps modifications. Any thoughts? Oh, of course, we would. Because membership has to approve the project, regardless of where the money comes from. For example, let's say that I wanted to put a swimming pool at Raza, and I had a swimming pool company that would pay for it. Or maybe it's let's go with the swimming pool. I couldn't just do that. I need membership approval to get the project approved, regardless of where the money comes from. And we are very fortunate to have very generous members that are putting money up. And if you think about the things that Bob was saying, that how we could utilize the Knoll Observatory, it's tremendous. And we're that close on getting it passed. Okay. There's another option. Yeah, that's right. So does that answer your question? Okay. Yes, sir.
Family membership or not a member, just a question. I'm a treasurer of another society. The 4,500, is that restricted to this project? And if so, is that the first 4,500 to be spent, such that 500 of the club's money may not need to be spent?
If you note the line items that were listed, one of them was miscellaneous.
The 660
estimated
something.
667.
Yeah.
So it may be that we don't need all of it.
Yeah. So that's where the club's money would be.
Yes, it's part of that 667.
Just curious.
So the motion that's on the floor is one that conflicts with the presentation we just heard. But it can be changed by membership. I'm comfortable with that. If membership thinks that we can move forward, we need to figure out a way to do that, because we have roughly 2,500 of that 45 already in hand. And so we have another 2,000 at risk. Seemingly it would come, but the board thought it'd be safer that we wait until we had the entire money in hand before we move forward with the project and order equipment. That is an issue. So the question was, we have the money lined up, let's do it. Okay. So my thought on that is, if we went forward and the additional $2,000 never materialized, the people who ordered it would be at risk, because the club would not pay for that. That's the only issue. We don't have all the money right now. I think there's a month or two deadline, or a month or two delay. Let me do this right. Maybe 2 to 3 months.
So that might cause an issue in a situation. We'll wait.
That's right.
How
How?
committal is it?
I think it's a pretty strong commitment for the additional $2,000.
Bruce, it's Robin. Can you hear me?
We hear you.
So I put something in chat, but I guess it wasn't seen. I really don't think we can change the motion unless the board goes back and changes this motion, because we met in executive session and this is our motion. And if we're going to change something, the board's going to need to change this motion.
My thought was,
we had to approve this all first.
right, but my thought is that because membership has the final authority, membership could change the motion.
So we had to have board approval for the expenditure first. And this is the motion we came up with.
I'm still thinking that membership, if we have the quorum, if the quorum's needed, then membership can change the direction that of the motion that the board put forward.
Not sure I agree, but.
Okay, well, let's go with my idea, and if I'm wrong, you can fire me.
Going to decrease your salary.
Oh, again? Can't wait for my performance appraisal. DJ.
There's a group of 8 people working. Okay. So, and the whole objective is to make this as available to members of the public as possible. You get trained up, you get signed up, we can sign up, and everybody will have an opportunity to sign up.
So let me also interject here. Bob, why don't you explain to them about who owns the data and who has access to the data?
I'm sorry?
Well, let me talk about that. So if I understand, correct me if I'm wrong, but by the data that's collected by the Noble is club data. It'll be available to club members to process. Or you'll also have what will be available to the club members are the processed images. Bob showed the 5 items that were just talked about in What's Up presentation. And those data will be collected, and they will then be posted on Facebook, they'll be posted on our e-groups, you'll have them available to yourself. So that's one of the fascinating things that I like about this project is maybe you put a couple items in to be considered for imaging, and not all of them got selected or imaged, but you would have that data available to you. And process it, or look through it, print it, or process it.
No, that's good to know. I was also, that, and then also, thinking, let's say someone wants to look at, M310 out there. And then someone else is like, how do we ensure, we can get equal time, or sign up sheet ahead of time.
And there could be all sorts of objects or targets suggested, and it may exceed the capability of the scope we have in place right now. So those would get weeded out, and those targets that, and I don't know all the criteria, but that we can get good images from will most likely be selected. And that's draft, there's a lot of things that haven't been considered, but this is a good discussion point.
Yeah, I figured there's a lot of little weeds and fire details.
If we had a bunch of people wanting to look at M3 hypothetically, then somebody could just do M3 and everybody would have access to the data.
Right.
So, yeah.
Right. Question back here.
Yeah, the image is going to be copyrighted by the Fort Worth Astronomical Society.
That's we're working with the legal beagle.
Each question as it comes
And the reason I ask is because, somebody could theoretically take the image and submit it to something and get paid for it, but in fact it's
Right.
We're working
Don't have an answer to
To
that,
repeat
but
for
we'll,
online,
we'll be
the
working
question
on it.
is, are the questions going to be copyright for the club?
Say again?
I'm repeating for on.
Oh, I see.
They can't hear.
I have a question. So if time is of the essence, as it sounds it is, relative to potential for tariffs or not, and if the total project is $5,000, I'm sorry I don't remember Constantine's numbers, but does the club have $5,000 available to it for, thank you, available, does the club have $5,000 available to it to apply to whatever they want to apply to, or whatever we want to apply it to? If so, couldn't a motion just be, the club does this if we vote approval for $5,000? And if people still are motivated to give donations as of this is tough listening myself, as they've expressed that they are, then in that case, the club just does this for $5,000. If people donate back to the club, then the money goes back into the kitty anyhow. So if we have $5,000 to do this, why don't we just do it? But I don't know what our total bank scenario is.
So, yes, funds are available. And what we need to do is someone needs to make a motion that we can proceed.
So in response to the question, the funds are available. Currently, we have approximately $40,000 in the bank. The commitments that we have are for $4,500, two of which have already been submitted, and we're waiting for two others, and I think the other two will come through fairly quickly, but they didn't feel like they needed to until we have approval for the project.
One question related to that. The club has $40,000. The only thing that would be prohibited or inhibited would be if the club foresees that it's going to spend all $40,000 on something in nearby imperatives. If not, who would like to make a motion or is that something?
I've been trying. Are you ready? Mr. President, I make the motion that the club approve the procedure of going on with the Noble Observatory, figuring that the membership will come up with any money needed if we have to.
Thank you. So we have a motion. And we have three seconds. All right, so. Right. So, let's call the question? Yeah. Right, so is there any more discussion on this from the audience here? Anybody, any other questions online or comments? And how many people do we have online now?
14 still. Plus one is 15. This Jake, he is a member.
Mm-hmm. Oh. Okay, so we're ready for a vote. So all those in favor, raise your hand.
Yell yes.
Okay, and all those opposed? Okay, and no opposed.
I'll talk to you later.
Okay. Working it? Okay, unanimous. Okay. Very good, yeah. How about a round of applause? Okay, our deadline is 9:30. What's that? Oh, we had one opposition? Okay, so it wasn't unanimous. There was one dissenting vote. So this may be the last time I'm president, so we'll see. So we have a hard stop at 9:30. Any big issues?
I'm gonna be, I can post this stuff, for, outreach online.
Okay.
At Groups.io, so that it's available for everybody.
All right, that sounds good.
Yeah, we can skip that.
Right, and the only thing we had on legal is Simonson has organized a subcommittee to work on the changes to our bylaws. He's presented that to the board. The board approved most of it, had some questions, and Si's going back to work through it. So there'll be a bylaw presentation at our next meeting. That's essentially his presentation. So,
One real quick. May the 9th, it's a Friday, 1687. Mr. Ashford is coordinator this time. I'll send an email out in the next day or two.
okay. All right, so
Yeah, just mention on the microphone for the people online that I'm gonna post that on.
Okay, great. So all the information about our outreach activities that won't be covered here tonight will be posted online on eGroups. Was that correct? All right. And the other last thing is social after drinks after the meeting at, what's the name of the place? Yeah, social house? Okay, I've never been. I understand it's pretty good, but I just want to mention that. So that's it for tonight. Thank you all for participation and the lively discussion that we had. Thank you.